Rohit sir, please begin.
Good afternoon, all of you. I am Dr. Rohit Lade. I'm an assistant professor at Chemical Engineering Department, Parul Institute of Technology, Parul University, Vadodara. I invite all of you to this wonderful webinar on how to do quality research in chemical engineering by Dr. Neeraj Thakre. Dr. Neeraj Thakre is PhD from IIT Kharagpur under the guidance of Amiya K. Jana sir. And he is MTech from NIT Nagpur and BTech from Manit Bhopal. He has a wonderful research experience in modeling of gas hydrates at IIT Kharagpur. And he is a very good researcher in this chemical engineering field. I would like to invite Dr. Neeraj Thakre to this webinar, and I assure that everybody will be learning from him. Neeraj sir, you can start.
Okay, thanks Rohit for the introduction. So Dr. Rohit is my colleague, and we have worked together in VNIT Nagpur. So yeah, we had a good experience in working together. So thanks for inviting me for this webinar. So yeah, so firstly, thanks for the nice introduction, and the topic of this talk is how to do quality research in chemical engineering. So I have the experience of doing research from my MTech, and then I continued it in my PhD as well. So so basically, what is research? By the word, it says that research means searching it again. So so it is a detailed and careful study of something to find out more information about it. So if you are into a subject and you are studying it, and so because we have already the information available in literature or in books, so we so as we know that knowledge is the ocean. So as we deep dive into it, then we will find more and more. So there is no end. So we cannot say that okay, we have completed this research. No, we can only step it forward. Only one step we can do, and yeah, and we have to see what others haven't seen. So in this way, we can tell to the research community, this is the other part of the coin. So in this way, we can see the research, and whatever you do the research, so as I have told that it should be shown to the research community. So for that we have to publish it. So research is meant to be published so that the world can know about it, and they can do they can take forward that research to the next level. So so what is the agenda of this webinar is I want to tell the research practice. So I will give the example of my research, but I will not focus on the technicality of that. And so because many of you are doing research in different subjects or different topics, because chemical engineering itself is the ocean. So I will just tell what practice I followed for doing my research. So those research practices same for every field. So this webinar will be benefited for everyone. So what is the basic research practice? We can say that we have to know the problem. What is the problem? We have to first identify. So by that we can make the problem statement, and then based on this problem statement we can formulate the objectives, and then to reach these objectives we have to make one theoretical framework, like the science behind it, because we cannot like directly do the experiments without knowing the theoretical background. So because there are thousands of ways to do the experiment, so we have to um, design our experiment based on these theoretical frameworks, and then the methodology. And so in the methodology we have to design our experiment, and we have to follow the path, the experimentation which will give us the proper result that we want. And then we analyze our results and we compare with the existing results, and then we analyze the result, like our results, what they imply. If you are finding that by increasing some parameters, some other parameter, that the dependent parameter is decreasing or something, so why that is happening, what is the science behind it. So whatever hypothesis you have formulated in the in the theoretical framework, you will uh, you will either like you can say that yes, whatever we thought was correct, and you can say no, whatever we assumed was incorrect. So both is are the positive results only. Okay. So in the chemical engineering there are like various fields like sustainability and energy, biotechnology and synthetic biology, catalysis, reaction and engineering, polymer and soft materials. Okay, so basically what we see is chemical engineering is a blend of mechanical engineering, metallurgical, material, okay, then field of chemistry. So all things can be used here, and the biotechnology, nanomaterials, all these are the fields where a chemical engineer can do the research. Okay, so if we divide this research field into two basic like fields, then it is experimental and theoretical. And these two research fields are not independent, they are dependent. So uh, so I will tell my story that I was not that much aware, like in the theoretical background also one can do the research, and I did that. So in my PhD I have done no experiment, I have done purely theoretical, means sitting in front of a computer and I did the research all my 5 years of my PhD. So this information is very new to like a BTech guys and MTech guys. Like they sometimes they think that the research or the PhD can only happen in the experimental one, but that is not true. So in all this and if we are doing the research, then maybe the experimental research is already being done, and based on those experimental research we can do the theoretical research, and vice versa is also true. Like without the experimentation, some hypothesis can be published that if somebody will do this type of experiment, then without doing the experiment based on the theoretical knowledge or science, we can come to a conclusion that if we do this type of experimental study, then the results can be of this way. So both ways, like in the same thing, experiment or theoretical, they can come first. So in my PhD work, I choose the the theoretical research, and my area of research was sustainability and energy. So this is my PhD seminar that I have presented, but there I told about like what I did. But to you guys, I will tell you how I did this. So this is more important, I guess, because what we what anybody has done, they can tell, but you will not get to know that how this research is done. So first thing is like here you can see it is the why this topic. Like first thing that come in our mind is why we have chosen this topic. So we have to, like I have told you, we have to uh, first go through the problems, like what problem the world is facing. So as we know that the global warming and limited fuel supply, these are the major problems that the world is facing. So if you are targeting these problems, then your research will be automatically, it will be beneficial for a general community. Okay, so your research should not be like very confined, or it is beneficial for a very small piece of community, then your research will not be seen as that much useful. So I will suggest that you will choose a problem that is that we are addressing. It should be a like it is good to target like big problems that world is facing. So obviously, like if the problem is there, then there will be solutions. Like here we have the alternative energy sources. So these are the solutions. But these already available solutions, they have some limitations. Okay, so the high installation cost, low efficiency, and climate dependency. These are the uh, main drawbacks of these alternative energy sources or green energy sources, we can say. So the attractive solution is the natural gas. Okay, so this natural gas, it is not a green energy source because it emits the carbon dioxide. But as we know that this natural gas is having methane, which has the least number of carbon atoms. So here the carbon dioxide emitted to the atmosphere will be least. So here uh, it is a like trade-off between like the green energy sources and the conventional energy sources. So by this we are giving some solution, and we know that this natural gas is present in the form of hydrates worldwide. So here also we can see that we are targeting the world. Like here if we are giving some technology, so use this natural gas hydrate reserves, then it will be beneficial to the whole world. So yeah, this is the great thing if we will succeed in this field. So in this way you have to choose your problem. Like you do not do the research because you are like it is all others are doing. No, you have to like you have to talk to yourself like what you are doing, and it is beneficial or not. So after that you have to know like what is the thing you are studying. So uh, you have to know some science behind it, because if you are doing some research, you have to do the advancements in that. So you have to know what it is actually. So here the gas hydrates are like ice-like structure having small gas molecules entrapped into the cavities formed by water molecules. So in ice, like there is no space for the gas to entrap, but in the gas hydrates, the gases can entrap into the cavities. So the application of these gas hydrates are, we can see this energy production, this gas separation, storage, transportation, desalination of water. If you are making the hydrates, because these hydrates can be made above the ice points as well. Okay, so we can make the hydrate of this seawater, and this hydrate can be melted out, and we can get the pure water. So by that we can desalinate the water. And CO2 sequestration, we can sequestrate this CO2 in the form of hydrates inside this deep ocean. So these are some applications which are again again attracting the attention of the reader. Like whatever research you will publish, if somebody is reading your paper, then they will get convinced that by this technology you are addressing these many of problems. So because we are using our product in these many applications, so in industry we have to like tune our uh, tune the conditions, because this gas hydrate can be formed at different conditions. So by these compounds, if we add it to the reactor, then the formation condition can be altered. So we have to know the science behind it, like how much tetrahydrofuran is needed to drop down the formation pressure so that it can be formed under the atmospherical conditions. So based on that, we can formulate our objective, that we can formulate a thermodynamic framework so that we can model uh, the clathrate hydrate formation. Okay, so we are going more deep into that. Like here we are accessing the knowledge of like how these gas hydrates are forming and all that. So here you can see a football like a structure, and inside this methane molecule can be stored, like methane or carbon dioxide. So this is one type of structure, and based on the gas size and shape, different type of structures can be formed in the nature. So yeah, I will move to the literature survey, and before moving to the literature survey, I want to show that how to do the literature survey. So for that, okay, this is yeah. So for doing the literature survey, we have different publications. Like one is the ACS. I think you all know about this one. So our chemical engineering papers are mostly published in ACS. Then one very uh, famous one is there, like one is elsewhere. So these are the publishers. These are not the journals. Okay. So elsewhere. So if we and third one is the RSC. Like there are many publishers. These are not limited to these ones only. So I will tell you how to find the research. Okay. So I will go to these ones, and yeah. Publications. Yeah. So here you can see these are the journals. So these are divided based on the like fields. Okay. So if I want to do in the field of physical chemistry, then one journal is there. The journal of physical chemistry. So here some filters are there. Yeah. So like here. So this is the Journal of Physical Chemistry A. Okay. So these are the generals And yeah, so in that list of issues will be there. So this is a monthly journal. So in every month there will be one issue is published. And here you can see, like if I click on this June 30, this is the current issue. So this in we can say this is a in progress issue. So if I click on this, or else I will click on the published issue first. So this is the all. So these are the papers which we can go through. So if I open this paper, then you can see. So this information you are seeing, this is the public information. Like you can see without any subscription. So you can see the title, you can see the author's name and their affiliation, and then abstract. These all you can see. And to download these papers, you will need a special access. So I'm at my home right now, so maybe I cannot access these papers, but I will tell you how to read the papers as well. So here we will be having the abstract. So this abstract, in the abstract, we will be having a summary of this work, like what problem they are solving. Okay, and how they have solved. So some glimpse of that, not in the detail, and what are the key results that they are getting, and how it is benefiting to the general community. So this is the way. Okay, then I will move to so in my research, uh, like I wanted to do the theoretical research in this field. So I found like what thermodynamic models are already available. So here you can see I have chosen a basic model that is published in 1959. Okay, and I am using I'm trying to understand this model, what it is doing. So I found that like these are like if I want to calculate this theta, that is fractional occupancy, then I have to calculate this C, that is Langmuir constant, and this Langmuir constant is a function of ultimately these parameters, and these parameters are the interaction parameter, the molecular interaction parameters. So I had to find the mechanism to calculate these parameters, because this model is very sensitive to these parameters. So uh, so the idea came in my mind is that if I will give some proper mechanism to calculate these parameters, then it will be a beneficial research. So what I did is I thought of like existing methodologies that are available in the literature to compute these parameters. So we have different methods that are already available in the literature. So these are the most accurate methods. So in the previous slide, I have shown that these can be calculated by fitting to the hydrate formation data or second wheel coefficient data, or the QM method, like molecular methods. So these molecular methods are most accurate ones. So I have chosen this one. And then I have, so here I am boiling down my field. Okay. So here all the molecular methods are listed, so which are used. So here I have observed it, like uh, I have told you that, like we have to know the problem, where the problem is. So here I have seen that all the molecules that are used here in the quantum mechanical calculations, they are all the small molecules. No big organic molecule is there. So I have tried to find the reason, like why why the QM methods are now not used for the bigger molecules. So this is one of my research gap. So this is called the research gap. So you have found that for the bigger molecules or the organic molecules, there is no method available. Okay. Secondly, like I have shown you the lattice, the figures of the lattice. So there we have seen that it is very well organized. Okay, but if a guest molecule is coming inside these hydrate cavities, then these cavities may expand or contract. So so in the existing models, these methodologies uh, are not like not registered for these ones, like these larger molecules. So this is one of the research gap. So these are some, like we can say that this is a related research gap, because if somebody has not done the energy estimation for these bigger molecules, then obviously they have not come to the lattice energy for those bigger molecules. So if you are finding some basic problem, then solving that problem, you can solve all the related advanced problems. So in this way, you are solving not only like the advanced problem only, you are solving it from the root. So every application of this hydrate will use your study. So this is some quality that we can bring to our study. So these are all the related problems. So if I am addressing this problem, then all this in this all advanced problems, I can use my methodology and I can advance these related problems as well. So here we can see that some studies are available, but these studies are only available for the small molecules. Okay. And these are some fluid models. So in that also, I have tried to make some advancements. So yeah, I will skip this for now. So these are the total research gaps that I have formulated for my PhD research. So this first is the main root problem, and these are all the child problems, we can say. And based on this research survey as well, I have published one paper in the Renewable and Sustainable Energy Reviews. So in the research field, you do not have to do the experiment or do some theoretical thing only to publish a paper. You can publish the review paper as well. The review paper are published by the ones who have done the research in those fields and who have some sort of good knowledge in that field. So this review paper I published at the end of my PhD. So you can go through this paper and you can get to know that how to write a review paper as well. Okay, then yeah, based on the research of gaps, you can formulate your objectives, like you can address those research gaps by doing which things. So those things are called the objectives. So here, if I can calculate the anisotropic cavity potential, anisotropic means which depending on the directions, and to formulate a lattice distortion model for the promoter containing calcium hydrates, and the lattice distortion model for the refrigerant hydrates, which is again a big molecule. So here we can see that if I am saying the big molecule, then I am targeting the liquid promoters as well and the gaseous promoters as well. So based on that, I can do multiple research. So this is the trick like you can follow to do the research. And these are like to propose a non-monotonous lattice distortion model. So how non-monotonous? Because what the research community was doing, they were only analyzing up to the small range. So they were getting a single trend. But when I thought of like the bigger molecules, then my range of this uh, the size of the guest is expanded. So in this expanded one, I got a non-monotonous nature of this lattice distortion curve. So this is again a benefit I got to know. And yeah, for a mixture gas hydrates, an advanced mixing rule I have proposed, which were there for the vapor liquid equilibrium studies, but not available for the for the gas hydrate studies. So yeah, so this is one of the contribution. Yeah, then we can target our objectives. So here is the first objective, that is computing anisotropic cavity potential for the creative hydrates. So what I did is I took a single water molecule and a tetrahydrofuran molecule, that is a big molecule. Okay. So then I have tried in the different directions. So this one, this water molecule will be not moving anywhere. Only this tetrahydrofuran molecule will move around this water molecule, and it will rotate around its own axis also, so that we can document the interaction energy from every direction. Because if it is in this configuration, then the energy will be different. If I move this water molecule to here, then the energy will be different, the interaction energy. So we have to document these interaction energies. Okay. So based on that, I have found that I have 6,400 configurations by which I have to compute the interaction energies, some geometrical constraints, so that this guest molecule should not move out of the cavity. That is why we have restricted this theta and phi angle to the -40 to 40. So these are some constraints, and these are the quantum mechanical methods which are used in the in the literature uh, for the organic molecules. So here you can see I have not designed my own QM method and all that. I have borrowed some idea from the organic chemistry. Okay, because in the organic chemistry they were using these methods, and these methods are they were not computationally very expensive, and they were giving the good results. So you have to uh, find the problem also you will find in the literature, and the solution also you can find in the literature only. Just you have to bring that solution to your domain. Okay, so in this way I have borrowed this idea from the organic chemistry, and I have used these QM methods in my research in my gas hydrate field. And there I have seen that if I am using this double zeta valence basis set, here I will give some knowledge about this. In this quantum mechanical method, this spin component scaled MP2 method, this is a equation, you can say. This is a Schrodinger equation. And in order to solve this Schrodinger equation, you have to discretize it. So for the discretization, these are the method. So this is the double zeta valence basis set. So double zeta means it is the lowest in its family. So because we are using the smallest basis set, then it will be faster, but it will have some errors. So like basis set superposition error, basis set completeness error, because this basis set is not complete because of this double zeta, because triple zeta, quadruple zeta, all these basis sets are there. So we have to get rid of these errors. So for that, for BSSE correction, we have the counterpoise method. And for this basis set completeness error, we have found that here, this is the 6 zeta basis set. So this is a very high or very fine, fine basis set. So what we tried is we tried to compute the energies, and these black ones are the counterpoise corrected. These red ones are uncorrected energies. So if I am taking the average, so I can see that I can reach close to the accuracy of this higher basis set. So this is also not my idea. This I have borrowed from those research only. So I have applied these ones my compounds, and I have found that it is behaving the same. So yes, those theory can be also useful in my study. So so this is one of the outcome. And I have used those energies, and I have calculated the parameters that I have shown in the modeling. So here we can see that the methane, tetrahydrofuran, cyclopentane, for all these I have calculated the energies, and I have listed down, and I have calculated the fractional occupancy and compared with the experimental data. So this is the main part. When you are doing the theoretical research, then if you have the experimental data and you are validating your experimental results with the experimental your theoretical results with the experimental data, then your theory it will be validated. Okay, so you can say that whatever hypothesis you have made to formulate the theory, it is correct. Okay, so these are some results and validations, so that for the same validation, and so we can conclude from our research that the complete basis set accuracy can be achieved by analyzing these errors, and half counterpoise method will cancel out the effects of these errors and the validation part. So based on this research, I have one publication in the Journal of Physical Chemistry A. Okay, so then moving to the objective 2. So the same type of formulation, here I have tried to formulate the lattice distortion model. So for that, I have transformed this equation into y is equal to mx plus c format, like the linear format, so that I can compute these parameters which are for the lattice distortion and the height, and so I have used the technology or the methodology that that we have formulated in our previous objective to this. And here with the same study, we are calculating the parameters, and using those parameters, we are calculating the lattice distortion parameters that are the delta mu naught. And these delta mu naught, we are plotting against the size of the guest, and we are getting this type of uh, like uh, models. So here we can see that this RCPD, that is reference chemical potential difference, it is a function of Kihara hardcore radius. Okay, so this is one of the parameters, and so this is happening in case of the gaseous molecules. So this was already published. Okay, but we have given some more accurate results here. But here this was never published. So this is our totally new research, we can say, for S2 type of for the large molecules. The lattice distortion model was not available in the research field. So that is why this research got published in the scientific reports, that is the Nature Publishing Group. So if we are doing this type of research, then you can target to this big journals, like big impact journals. Then moving to the objective 3, the ab initio assisted lattice distortion theory for refrigerant hydrates. So for refrigerant hydrates, I have followed the same strategy. So here, theoretically, no change as compared to the objective 2. But here we can see the difference in the results. So here we can see that this delta mu naught is dependent on the epsilon. Epsilon means energy parameter. So in the research field, never this delta mu naught is correlated with the size parameter. Always it is correlated with the size parameter, never with the energy parameter. So what is our outcome here is, like, if you see these refrigerants, these are differing with the functional group, like the fluorine, the number of fluorine molecule is differing. And in the fluorine, we can say that the size of the fluorine is not important. The more important thing is the energy, because it is a very electronegative element. So here, so with that reason, we are getting the epsilon, the relation with the energy parameter. So in this work, what I tried is, like, when I got this delta mu naught, so I tried to correlate it with the size parameters, but I was not getting the correlation. Okay, so I suddenly tried with this epsilon, and then I got the correlation. So after that, I thought, why this is happening? Okay, so then I found a good scientific reason that, okay, in these compounds, they are differing with respect to the functional group. Okay, so not the size, like C2 S6 or C3H8. So they are differing with the size. So their interaction energy will not differ that much. But here it will the energy parameter is dominant. So this is our main outcome of this research. Okay, so we have validated our proposed research, and this publication, this research work is published in the AICHE journal, which is again a very good journal in the research field. It has a very good reputation. So moving to the objective 4, non-monotonous lattice distortion theory. I have already talked about this because if I'm taking a wide range, because with my methodology, I can enlarge this range. I can calculate the interaction energies between the molecules in the larger domain as well, larger size range as well. So here we can see that uh, yeah, so this is a non-monotonous curve. So here these are this section for the small molecules, and this section is for the larger molecules. So here we can see that our cavity is shrinking, and here our cavity is expanding due to the molecular interaction. And why this is shrinking and expanding, I will tell you by this graph. So here you can see that in this, like this is the zero energy line. Okay. So so these points are the negative energy, means attraction energy, and these points are the repulsion energy. Okay. So if a molecule is smaller, okay, in the cavity, then it will be in a larger enough distance from the water molecule. So it will be in this range. So it will attract the water molecule. So the cavity size will be less. Okay, like it will shrink, try to shrink the cavity. But if we have the larger molecule, then what will happen? Some of the atom will fall into this region, because that larger molecule is fitting into the cavity. Then this repulsion energy also will be there. So it will expand the lattice. So in this way, so like this hypothesis was in my mind, and with this study I could say that like my hypothesis was correct. Okay, so by in this way I have proposed a new equation. Earlier only this term was there, but I introduced one more term, that is defining the variation, the positive variation, negative variation as well. Okay, so this is the validation, and based on this work, I have again a publication in the Journal of Physical Chemistry 8. And this is the objective 5, in which I have introduced some complications in the vapor phase model. Earlier, I was doing in the only for the hydrate phase. So this is a vapor hydrate liquid equilibrium, 3-phase equilibrium. So I have tried in this work to advance the vapor phase model as well. So here we can see this is the mixing rule that was available for the it was available for the VLLE calculation, but not for the hydrate field. So I have introduced this one, and I have validated this, and these are the results that with my proposed model I am getting very less magnitude of error. So that is again validating our proposed research. So this research was published in Applied Energy. It is also a very reputed journal in the elsewhere publisher. So these are the general conclusions that I have made during my PhD research. Then the future scope, because as I have told you, like we cannot say that we have completed our research. No, it will never be completed. It will never be completed after thousands of years as well, because the advancements will always go on. So whatever research you have done, you have to open some fields to the fellow researchers as well, because like they can know that in what what are the fields where we can do the research. So these are uh, some research gaps we can say, which the fellow researchers can target. And this organization of my PhD thesis, these are some acknowledgements to my professors. And this is the real picture of the hydrate that is digged from the ocean floor. Thank you so much. This is the publication from my PhD thesis. So this, my research was not limited to my PhD thesis. I have spent 5 years in IIT Kharagpur, not 5 years, 4.5 years, I can say. And in that, I did some collaboration with my lab mates as well. And I published some other research papers with them in some other fields as well. Here you can see, this is the uh, research publication in the field of process control. And this is a fuel cell. Okay. So in this way, we have done research in the different fields as well. So I hope this webinar is beneficial to you. And if you have any questions, you can reach out to me. And yeah, so that is it from my side. Thank you so much. Is there anybody? I cannot hear anybody. Okay. Thank you so much.